Okay, morning everyone. I think we can start this session. And as usual, if you have questions that cannot be asked due to time limit, you can also follow up on Slack channel. So let's start. So today, the first talk is from Jing. Jing, can you hear us?
Yeah, I can hear you.
Okay,
Hello?
so please go ahead.
Oh, okay. So I'm very glad to give a talk here in the morning. And my name is Jing Shu from Institute of Theoretical Physics, Chinese Academy of Science. So today I will talk about constructing the massive on-shell operator basis. So this is my work in collaboration with my student Ziyu Dong and also my former postdoc Ten Ma, now who is in Israel. So first, why we should think about the EFT? So EFT actually has a wide applications nowadays on various subjects. They can actually studied from the high energy physics to QCD and even apply to things like condensed matter physics, atomic and molecule physics. So in my eyes, it's sort of really the kernel of the modern quantum field theory. And already in our high energy physics, there are already marvelous applications to many different branches. Like for instance, the flavor physics, how the operators are running, and also the precision electric weak physics, that how we constrain various different electric weak operators. And also we may do two different dark matter categorizations, different kinds of dark matters. And especially nowadays, we are actually searching the new physics at HEC, and probably in the future about we have the Higgs factory. So basically, we really need the precision Higgs measurements, and this can really um, help us to understand the new physics a lot if we use the effective field theory approach. And so they are important. And more interestingly is that we actually noticed there are some interesting progresses on these EFT frameworks and calculations based on new methods. And this is the on-shell, the sort of the in the spirit of this on-shell amplitude method. There are actually many different applications for this on-shell amplitude methods and on the EFT stuff. So I just mentioned a little bit, but I'm pretty sure that I didn't mention all of them. So first, it can be used for the very efficient methods EFT calculations. For instance, in terms of EFT, we can calculate the RG roundings, and also we can actually do the partial waves, and also find the selection rules according to the helicity selection or the angular momentum selection, for instance. And also we can construct various different special EFTs due to the solved theorem, like for instance, the DBI, collinear, and other things. Besides that, there are also many other applications, things like positivities or like sum rules in the low energies. But all of them are very interesting and sort of has some collections with the on-shell spin helicity method. So today I will talk about one special topic, which is one of the things that I've been working on, not all of them, is the actually efficiently constructing the operator basis. And in our old paper and together with other people's, actually it is point out that for various different operators and all of those independent operator bases, they can be one-to-one corresponds to the unfactorizable amplitude basis. So in terms of, and those amplitudes actually, they are, if they are on shell, they are usually can be easily get rid of the equation motion. So especially for the massless amplitude, this becomes trivial, that you just all the momentum acting on external field becomes zero. And besides this equation motion, there's another thing called the integration by parts, which is that you have to the total derivative of the the operators is 0. So in this case, they correspond to the so-called momentum conservation. And this momentum conservation is not automatically built in when you write down all of those amplitude bases. And interesting is that you actually can find there's for endpoint functions, you actually can find there is a UN symmetries for the external particles there if they are not identical. And in this case, one can deal with the momentum conservation. And if they are identical, you just have to input some permutation group to deal with it. Just things become more complicated, but it's quite doable. So the amplitude basis is really just some kind of special UN representations based on the endpoint functions and also the Lorentz symmetry. And all of those have been already implemented in the automatic computer programs based on this paper, and also there are some other following papers. But there is another thing which probably we have to also want to think about is that although the massless the operators based on the massless field is very useful, but it's not everything. In practically, we really have to deal with massive things in many cases. So in this case, what happens? So let's just first just have a very small review on the difference of massive amplitude and massive field and massless field. So for the massive spinors, its little group is the SU2 instead of the U1. So in this case, we can write down the momentum according to the rules which are basically invented by the Nima, Yuting, and their collaborators. So in this case, they are the actual label I, which are the SU2 indices. And these actual SU2 indices will be the difference. And in this case, for instance, for spinors, you actually have these quantum numbers. So these quantum numbers are the SU2L cross SU2R. They are just the spinor indices for the Lorentz groups. And you can see this right-handed, this left-handed, and also there's another thing which is actual SU2 is this actual little group index. And for massless spinors, this actually is trivial because this I is really just a phase of the U1. So you can just have these phases, and then you have this spinor product, which are just invariant under the little group. So in this case, these external massless particles, the really important one is their helicity. So they only transform according to their helicity. And for the massive ones, actually, they also have these actual indices according to the SU2 symmetric representation. So what happens is that you get all of them out, then they can be actually they also in the end give you a symmetric representation of the SU2. And this is basically the rules for how this massive spinors transforms. And so basically, I mean, the thing that in the old days when in our paper, in any amplitude, you actually can write down massless amplitudes according to the rule that the first part is the external legs, which are basically the little group charge. And there you can see them are just these different brackets. And also you can see there the actual piece, which is the Mandelstam variables. And this polynomial of Mandelstam variables, which doesn't have the poles, is this little group neutral part. And then you also have things like a gauge structure. And if you have identical particles, you have to deal with the spin statistics and other things. And the amplitude basis just corresponds to the leading interaction of the operator. This actually means that, for instance, when you write down a covariant derivatives, what happens is that you just forget about all of those actual pieces for the gauge bosons. You only write down the part which only have these derivatives. You write down the f mu mu as the partial derivative and the covariant derivative as the partial derivative. And similarly, you can just to find the amplitude basis according to their independent unfactorizable amplitude. For instance, for the three gluons, you have these contributions. They have different results. They just correspond to different operators. So when you actually want to deal with the integration by parts, and the reason is that when you write down those operators, they does not guarantee that the operators actually are completely independent, because you didn't plug in explicitly the momentum conservation condition. And in terms of momentum conservation condition, as I have said before, there is one trick which is use the UN symmetries actually to automatically guarantee these massless spinors. So in this case, you write down the massless spin not only according to their Lorentz symmetries, but also actual symmetries which are related to the n external legs of the particle. And in this case, you write down the Pavlovian spinors as the basis of these UN representations, and also the left-handed spinor and right-handed spinor have different transformation properties. And these papers are the original papers which talks about how to deal with those reduced Young tableaus. And I want to talk about those in great detail. And so in this case, what happens is that you actually have these operators which you basically write them as the holomorphic case and anti-holomorphic. And naively, you may think about them as the left-handed fields and right-handed fields, right-handed spinors. And all of those spinors, when you constructing operators, you just cross them, and then you are get the total tensor structure. And finally, those tensor structures actually are called they correspond to the different independent operators. Things become actually pretty straightforward if they are purely left-handed spinors or right-handed spinors. And the tricky thing and the interesting thing is for those so-called non-holomorphic cases, that when you have this left-handed spinor and the right-handed spinor, you time them together, you can use this Littlewood recascent methods to actually get the independent tensor structures. What happens is that you are finding interesting is that if you just completely follow the rule of these writing methods, all the IBP redundant part will automatically deal with or just kicked out. And similar things with things are related to the Jordan's identity and other things like field identities. So what happens is that this integration by part redundant part will be automatically taken care of if you use this rule of the Young tableau method. And this is pretty interesting and very important in the sense that if you actually use this kind of methods, you really can just first they are always guaranteed that you get the completely and correct results. The operator, all of those spaces are completely independent, and they also are completely they are complete. And in our old papers, and I think Jiang Hao had already talked about that. So basically, they are actually nowadays they are completely practical. They apply to standard model effective field theory and maybe some fermion effective field theory and what have. And one can deal with other things like the permutation group and also gauge group and other things. So everything is completely practical, and one can just use them for practical calculations. However, there's another part, as I have said, is a big part that needs to be dealt with. Is that what happens if your operator itself actually is massive? You actually have this massive external field, and then how do you deal with it? The massive field has a different little group representation, and in this case, can you also just factorize them and also use the similar methods of these group structures to deal with all of those massive operator bases? And the answer is yes. And definitely, as I have said, massless amplitude is interesting, but sometimes it's not completely, I would say it's not everything. For instance, in the electric weak theory, if you deal with the electric weak symmetry breaking phases, and in this case, you have to deal with the massive case. Of course, in some sense, one can just always write down the standard model effective field theory and also writing them just doing the expansions of the Higgs insertions. This is important, but however, on the other hand, in some cases, for instance, you deal with the three massive gauge bosons, and if you want to say that I want to calculate the things in terms of standard model EFT, and in this case, you probably have to just have these Higgs insertions up to like say 4th power, 6th power, whatever, depends on your required precision. And if your fundamental cutoff scale is not so high, this expansion is not so efficient. And also other things like I think Nathaniel will talk about that sometimes they have different branching structures and they have
Hello, could outside still hear us? Anyone on Zoom?
No.
You can hear me, but not Jing, right?
Right.
Okay. We need to ping Jing.
hello.
Yeah, we can hear you.
Okay.
And also your slides.
Okay. So for the massive amplitude basis that we can factorize them into the massive little group charge part, which are the part that have these SU2 indices, and also the part that are neutral. That all the SU2 indices are actually contracted. So in this case, in the first part,
Hello, can you still hear us? Anyone can hear? Okay.
Oh,
Can you hear me?
hello.
Yeah, we can hear you.
Okay. So can I go on? Hello.
Sure, please go on.
Okay. So in this case, so the first part which I called the little group, massive little group tensor parts, they just can be classified according to their different SU2 right representations. So in this case, what happens is that you write down all the particles, and each of the particles, they are just according to their spinor representations. And so in this case, for instance, if you are a fermion, you just write them as the fundamental of the, and also for things like the gauge bosons, you write two of them, and they are little group indices. They are just according to the rule. They are just use these symmetric tensors to factorize them. And the Higgs, for instance, is just trivial. So in this case, when you writing down the psi prime ZH, what happens is that you just have these psi prime, which are the particle 1, particle 2, and the particle 3 with the Z, and they are the symmetric tensors. And then by doing this, you are just using the same kind of group factorization. So you then have all of those 4 parties. And according to these 4 different Young tableaus, you just write down the corresponding amplitude for these linear polarization tensors. So for instance, as I have said, you write them like this, and then basically you have all of those things. What happens is that the 1 and the 3, they're anti-symmetric, while 1 and 2 are symmetric. So this means that actually the 1 and 2 actually are symmetric under each other, and the 1 and 3 and 2 and 3 are anti-symmetric. So by doing this, you just write down the possible permutations according to these symmetric anti-symmetric structures. So in the end, you can write down the part of the part that are sensitive to the little group indices. The tensors are basically like that. And the other part is the neutron part. And the neutron part, although it's sort of the same as what I have said before in the purely massless amplitude basis, but they are slightly different and tricky things. So in this case, you write down them as they first they have to be massive little group neutron, means that when you have these different brackets, they actually have to have all of them, and they have to contract it with each other. So in the end, these big I indices are completely contracted. And when they are completely contracted, you can just forget about this little group index and sort of naively treat them as the massless fields. And so basically in this case, what happens is that you just you can write down the operators in just like the massless limit, and then in this case you have actual Lorentz spinor index, and this spinor index has to contracted with the little group tensor part, which is the old part of this. So in this case, so then you have this special UN representations, and then you have this integration by parts, which is just can be killed all of them, and then you have this massless limit. When you have this equation motion, you have this one-to-one correspondence with then deal with the original massive case. What happens is that in this case, so you basically have to rewrite these PIs in terms of all of those spinor index, and then you go to this massive little group neutral part, and each of them they are just corrected with each other by the equation motion. And in this case, they are just has a difference of these mass perturbations according to the equation motion. And so that you can also write down the general shapes. They are pretty similar as the case for the massless case. And in the end, one has to prove that the case that you combine with the little group neutral part and the little group tensor parts actually are purely independent. And I want to talk about this, and you can go to my original paper to read them. So finally, I will just have a very small examples of these applications, which we applied this, for instance, for this WWZ amplitudes. So in this case, as you can see, they are all of them vector fields. So you have all of these symmetric spinors, and they are times each other, and then you have these 7 different structures. And those 7 different structures are the basis of these massive amplitudes. So the first part, for instance, you see this, and then according to the rule, they become something like that. However, in this case, you didn't see any kind of spinor indices. So in this case, the correspond to contraction for the little group neutral part is trivial, that it's just 1. And the second part is that you can see those kind of things. So you can see these 2 indices actually they don't have anything to contract it with them. So you have 2 actual indices of this alpha dot and alpha dot prime, and this actual index has to be contracted with the little group neutral part. So in this case, you can have 2 of the other particles which also have this alpha dot and alpha dot prime, and they will be contracted with them. However, you also need some total epsilon tensors, and these total epsilon tensors will be used to contract everything, so that in the end the result is the little group neutral. And so in the end, this I1 and I2, you can plug in the possible particle information, so that this epsilon tensors is non-zero. So in this case, in the end, you can write down the corresponding massless limit case, and then very naively you just brutally insert these SU2 indices, which you go from the massless case to the massive case. You brutally insert all those big I's and the big J's, and in the end you get the amplitude like that. And one can also calculating the other corresponding group structures, which I just won't talk about. So in the end, you have all of these. They can be just completely one-to-one correspond to the papers for the purely massive amplitude calculations. So finally, I will just give a summary. So here we just propose new methods which are can completely construct the massive amplitude basis. And after that, we are really just free of all of those EFT operators. So sort of the writing down the EFT operator basis is no longer sort of, it's sort of, I would say, completely fixed problems. Just you just use Mathematica and probably use some machinery codings, and then it's not a big deal. And we have nowadays trying to implement this into the purely computer programs to automatically formulate all of those things. And I have said, especially useful. These are especially useful to deal with things that with multiple massive gauge bosons. And this is, I would say, this is really the part that has, I would say, this is really the part probably that are not really, people didn't really deal with them very well. However, with our new methods, I think that for the massive gauge boson interactions, so we can just automatically write down all of them. And I can see that probably, for instance, one can apply to other EFTs like Higgs effective field theory and other things. So I will just stop here. But definitely, I would say this is interesting. Probably can also be used to things like the loop calculations, other things, because in many blobs of these loops, they are just the blobs of these different massive amplitudes. So all of those things, I think that they really has a very exciting future, future extensions and applications. So I will just stop here. Hello?
Yeah, we can still hear you. Thanks. All right, thank you for your nice presentation. Let's see, do we have any questions from the room here? Okay. Just a minute.
Hi, Jin. This is Jain. It's very nice talk. I have maybe a naive question. So, I mean, in constructing this amplitude basis, is it sufficient to just consider polynomials of spinor product? I mean, for instance, in the standard model, you can have like a contact interaction, but still have something in the denominator.
Right. So this is a very good question. Actually, it's also sort of the philosophy. So I would always believe that the best or the relatively so that actually I believe there is a very big philosophical question. Actually, this goes back to the old days of the Wilson. So we just write down those operators according to their dimensions. But when you really are actually doing the amplitudes, what really happens to you that you classify every amplitude in terms of the number of the external legs, and the number of external legs actually are the part that gives you the spinor information, while the inside is just form factors, which, as you have said, is really just a polynomial of the London state variables. So in principle, actually, for because nowadays we always write down everything in terms of this EFT approach or the operator approaches based on different dimensions. But practically, I would say it's more useful. Actually, you just directly write down in terms of the outside external spinor information plus the polynomial of the London state variables. And these polynomials of London state variables are really just the part, or the kernel that has nothing to do with your probably Northern symmetry and other things. So yes, I mean, when you write down all of those things, you really write the corresponding operators in terms of the first spinor part, and the second part is the polynomial. And practically, if you deal with dimension 8 or dimension 6, then you just truncate at the different powers of those polynomials. Hello?
Okay, thanks. Yeah.
Okay, thanks. Do we have any question from Zoom? If you do, please raise your hand. So I don't see any. All right, then let's thank Jing again for the nice talk. And we move to the next one. So the next talk is from Nathaniel. Can you hear us?
Yes, yeah, hi. Let me share
great.
my slides.
Hi. Okay.
All right. How's that?